All right, so these are our notes on electron configurations. We're going to be learning 4 methods to represent the electrons in an atom or an ion. Those 4 methods include the off-bal or orbital diagrams, orbital notations, electron configuration notation, and noble gas or shorthand notation. So we'll do a quick review of quantum numbers and what they mean. Principal energy level is symbolized by N, assigned values 1 through 7. Energy sublevels get the symbol L, assigned S, P, D, or F. Orbitals or magnetic number is M. S sublevels have 1 orbital, P have 3, D have 5, F has 7. Spin gets the symbol S. If there are 2 electrons per orbital, one has an upspin, the other has a downspin. Because modern atomic theory describes the atom in a much more complicated or complex manner, we use electron configurations to describe the arrangement of electrons around an atom instead of drawing them like we would in a Bohr model. 3 rules we use to help us determine electron configurations. 1 is the off-bal principle. 2 is the Pauli exclusion principle. And 3 is Hund's rule. The off-bal principle, I call it the lazy electron principle. Each electron occupies the lowest energy orbital available. So it's like filling the hotel from the bottom up. The Pauli exclusion principle, I call this the spin rule. A maximum of 2 electrons may occupy a single orbital and they will spin in opposite directions if there are 2 in there. Hund's rule is known as the find your own room rule. With this rule, if 2 or more orbitals of equal energy are available, electrons will occupy them first. So they're going to go to the lowest energy orbitals first before filling with the same spin. Before filling them in pairs with opposite spin. So for example, if I was filling the second energy level, P sublevel, I would have 3 orbitals. If I had to do 4 electrons in this sublevel, I would fill 1, 2, 3. Notice they each get their own room or own orbital before I start filling them with the second, with number 4 here. And that would go in the opposite spin according to the Pauli exclusion principle. Okay? So remember, spin is denoted with an up or a down arrow when filling orbitals. So an off-bal diagram or an orbital diagram is kind of the best picture we have that shows the building up of electrons in a diagram or in a picture format. We put 1 S at the bottom and we show how the potential energy increases as electrons move farther from the nucleus and into higher energy sublevels. So the lowest energy level available is the first energy level. That is the one closest to the nucleus. A 4S is going to have lower energy orbitals than a 5S, so those would fill first. A 3D has less energy than a 4P. Okay, so a 4P is going to have more energy, and we can use our periodic tables to help us figure that out. So below we have an example of sodium in an off-bal diagram. You can draw your off-bal diagrams with blocks, with boxes to fill in the electrons, or you can use lines. So the way I would do a sodium is I would first pull out my periodic table and I would find sodium on the periodic table. Sodium is number 11. That means sodium, a neutral sodium atom would have 11 electrons. Sodium is in the S block, 3rd energy level, so that tells me how far I need to draw my off-bal diagram. So the highest energy orbital available in sodium is the 3s. And I would start filling till I get to 11 electrons. I do 2, 4, 6, 8, 10, and then there would be 1 electron in the 3s. Okay, so let's try oxygen. So the first thing I would need to do is look up oxygen on the periodic table. Oxygen is number 8. Therefore, oxygen has 8 electrons total. Oxygen happens to be in the P block, 2nd energy level. Okay, so I would go ahead and write down that oxygen has 8 electrons, so I know how many I need. I would start with the 1s. then I would draw my 2s, and then I would draw my 2p, because that is the energy level, sublevel that oxygen is found in. Now I would start filling until I get to 8 electrons. 1, 2, 3, 4, 5, 6, 7. So right, 1 for each room, and then 8. This shows me that oxygen has 4 electrons in the 2p. I can check that by looking at my periodic table. Oxygen is the 4th element block over in the 2p. Okay, so that helps me check that I have the right number of electrons in the 2p, and everything below it would be full. Okay, we're going to try iron. Iron is number 26 on the periodic table. It is in the D block, 3rd energy level, so that's as high as I'm going to draw, and I can even count how many arrows or electrons I will need in the 3D. 1, 2, 3, 4, 5, 6. Everything below that would be full. So I'm going to start with 1s, 2s, 2p, 3 lines there, 3s, 3p, 4s. Now I go to 3d, which gets 5 lines because there are 5 orbitals in a d sublevel. Total of 26 electrons. So I'm going to fill these in real quick. And these are my quick arrows, like a half arrow. Okay, so I'm up to 18, 20, 21, 22, 23, 24, 25, 26. I'm going to the 3D with 6 electrons, and I can check myself because iron is in the 3D, and it is the 1, 2, 3, 4, 5, 6 block over in the 3D, so I know I'm correct. Okay. At this point, you would want to turn to page 15 and do the practice on off-bell orbital diagrams. Okay. I'm going to keep going in the notes, so you might want to pause and do that first. And we're going to be going to orbital notation. Orbital notation is very similar to an off-bell diagram, but it is not an actual diagram. It's not a picture. It shows energy level, sublevel, orbitals, and spin of electrons, but it's not showing the building up from lowest potential energy to highest. So for example, magnesium has 12 electrons, so I would fill this just like I would with an off-bell diagram with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. So I just write horizontally the energy levels and sublevels. So let's try another one off to the side. So here's another practice one. Let's try fluorine. Fluorine is number 9 on the periodic table. It is in the 2p, and it is the 5th element in. Okay, so I know I need 5 arrows in that 5th one. So I would start drawing 1s, 2s, 1, 2, 3, 2p. Then I would fill 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I am done with fluorine. Okay. All right, electron configuration notation is the most common way that we write electron configurations. So it's going to indicate the arrangement of electrons, and it's more commonly used in an off-bell or an orbital notation. So a typical electron configuration notation is going to consist of an energy level, a sublevel, and a number of electrons. Okay, and it's going to be listed in a format that looks similar to this. So you'd have your number for your energy level, your letter for your sublevel, and then your number of electrons. Okay, so this is actually helium. Okay, so the number indicates the energy level. So that first number is the energy level. Okay. Sometimes we call this the principal energy level. Okay. The letter that comes after it is the type of sublevel, and that's going to have the letter S, P, D, or F. A superscript that follows the sublevel indicates the number of electrons in the, when you scratch that out, sublevel, not orbital, okay, because we're not breaking these down by orbitals. So 1s2 means that there are 2 electrons in the s sublevel of the first energy level. Okay, so this is helium. So if I go to 1s2, 1s, and then I count over 1, 2, that lands me on helium. Okay. So you're going to write an electron configuration and determine the total number of electrons. Use the off-bell process. So use your periodic table and build from the bottom up. The sum of the superscript should equal the total number of electrons. So let's try silicon. Silicon is number 14 on the periodic table. One thing I like to do is go ahead and find silicon and see that's in a 3p and it's the second block over. So the last thing I write is 3p2, and I can even jot that down. We always start with 1s, and everything below it is full. So I'm going to start with 1s2, 2s2, 2p6, because a p holds a total of 6 electrons. Then I would go 3s2, 3p2. Then if I add up all the superscripts, there's 10, 12, 14, that gets me to the number of electrons. Okay, let's try zirconium. Zirconium is number 40 on the periodic table. It is in the 4D, and it's the second one over. So the last thing I write down is 4D2, okay, with 40 total electrons. So we're going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, now we go to 3d10, 4p6, now we have to come here to 5s2, now we land on zirconium, 4d2. Okay. All right, our next one is terbium. Terbium happens to be in the F block. Okay, it is number 65. So the last thing I write down for terbium is 4F, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to write down 4F8 as the last thing. Okay, what's kind of weird about F block elements, so you have the F block, you have to get to the 4F, because if you look here, this is 58, you have to go through electron number 57, which is a 5D. So any element that's in the F block is going to have a 5D1. So any element in the 4F or in the 5F is going to have either a 5D1 or a 6D1. Then you will write your F block elements, okay? So starting with 1s2, this one will take a while. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now we're on 5s2, 4d10, 5p6. Now we're at 6s2, and this is where it gets weird. You're going to write 5d1, then 4f8. Okay? All right, so radon. Radon is number 86 on the periodic table. Okay? Radon is way out here. It is an element that actually falls after the F block. So to get to radon, you have to go through 6s2, 4f14, 5d10, 6p, and we'll go all the way over here. So you can write your S's, then your F's, and then come back up and do your D's. Okay, and we're going to go all the way out to 6p6. So I'm going to jot that down so I know where I'm stopping. So we're going to take a minute to do this. So we're going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, coming down here, 5s2, 4d10, 5p6. Now we're at 6s2, and we're going to go ahead and fill our F block. 4f14 come back up, fill our D block, 5D10. Now we're going to go over here to the P block, 6P6. Okay. All right, so we're going to stop here for now, and you can go ahead and do the practice with orbital notation and electron configurations.